Okay, the final step, now that we have our mesh, is to move on to Fluent. And so Fluent is not specifically listed here, but setup, solution, and results all occur within Fluent. Now, here's one tricky point, which is that the mesh here, if you look at it, has a lightning bolt. The mesh wants to be updated. For whatever reason, it doesn't do that automatically. So it takes a little while. And there it is. Okay. So now under setup, really what we want to do is launch the setup, and you right click and edit. It's 2D by default because we specified that in the geometry. The double precision is a good one to use, and then the other settings are fine. Double precision is just the precision with which the numbers are stored. Okay, so there's our mesh. We're going to get some warnings here. For example, it's going to say that the use of axis boundary condition is not appropriate for a 2D, 3D flow problem. Okay. That is because we labeled the bottom boundary as axis. And what we're actually going to be doing is, in essence, we've got this 2D thing, and we're going to revolve the geometry around this axis to simulate a 3D problem. To do that, you click Axi-symmetric. Axi-symmetric swirl is another option for cases where, in fact, you do have fluid swirling around the pipe. But we don't need to consider that. So this is all we need. The next thing is to do a check of our mesh. So up here, these are buttons relevant to mesh, and we'll check it, and it's fine. This scale thing here is one that's a little bit interesting in that it's always nice to look at the numbers here and make sure that in fact it really is 7 millimeters long and 0.7 millimeters high. And we see that it is. If for some reason we wanted to display the mesh again, we would click this button. And in fact, if you want to just see the mesh on the walls, or just see the walls themselves, then you remove the interior surface body. Report quality, sure, it's something you can do. The numbers aren't really that meaningful, and if you have enough elements, then the quality will be good enough. So what we're going to be doing is basically going down this list in order. The next one is models. For most of the class, we won't have to worry about this at all because all of these options are turned off except for viscous, and that's already set to laminar. And we're going to assume laminar flow in all of our models. You can do turbulence, but we just won't worry about that. Okay, under materials now, you only have two choices: solid aluminum and as a fluid air. We want water. So we click that button that says Create Edit. And then we click this button that says Fluent Database. Scroll to the bottom and there's liquid water. Copy, close, close this, and now there's water liquid. You still need to go in there and select it though. Cell zone conditions, basically the surface body, this is a name that means the interior. Fluent picked that for us, we didn't specify that. But the only thing you want to check is that the type is fluid. The other option is solid, and clearly this is a fluid flow problem, so we want fluid inside of our pipe. The boundary conditions then, interior surface body actually refers to, again, the face, and we don't have to do anything with that. The walls, remember the walls are the top surfaces, and they are automatically set to a boundary condition type of wall. And if you wanted to, you could change it into a moving wall, or you could specify that there was some specific amount of shear present at the surface. But these are hard walls, so the no slip condition is fine. In fact, all the defaults are fine there. The axis here is defined as an axis. There's really nothing we can do, nothing else to add there. One important thing is the axis must lie on the x-axis, or at y equals 0. This is very important. If we had designed our geometry where the bottom edge here was not at y equals 0, the whole thing would fail. Okay, we did that properly in the geometry, but I didn't actually mention that part. But it's an important thing to keep in mind. For the inlet, what we're going to do is we're going to set the, not a velocity inlet, but a pressure inlet. We change it, and we need to set a gauge pressure. And for this problem, 10 pascals is actually sufficient to give us a pretty high flow rate. Okay, we don't need these things. Solution methods, we're going to use the defaults. Solution controls, again, defaults. Monitors. Now this is going to specify a convergence criteria that's going to say when we actually stop the simulation. And the default values of the residuals, you can see them by editing, are actually quite high. So we're going to change these to 10 to the minus 12th. Solution initialization is quite simple. You click initialize, and now the simulation is ready to start. We'll skip down to run calculation. You can check the case if you want. No recommendations. So it's ready to go. The number of iterations is set to 0. One thing that happens is that people forget to change this and they're clicking calculate and nothing's happening. We're going to set this to 1,000 and calculate. Here it goes. Okay, these 3 lines here are the residuals. The idea is that you start off with no flow throughout the whole domain. The pressure is actually set to 0 as well. And the inlet pressure is then set to whatever the boundary condition is. So Fluent then modifies the values of pressure and velocities throughout the region of interest. And it keeps moving them until you get agreement with the Navier-Stokes equations and the continuity equation. How far off you are from satisfying the continuity equation is the white line. And then these velocities here are other convergence criteria that are calculated from the Navier-Stokes equation. Okay, so 1,000 iterations, 1,000 guesses in an incredibly short amount of time. We can, in fact, calculate again. The nice thing about Fluent is that you can always restart your simulation and it picks up from the last point. The only way that you lose your calculations is by either the program crashing, the computer turning off, or you reinitialize the solution. Okay, so we've met our convergence criteria. It looks like it could go even further and give us even better values, but you know, this should be good enough. To see the solution, we can go to Display, Graphics, and Animation, or we could just go down here, either way. And we're going to want to look at contours. Setup. Contours of velocity are really enlightening. You click Display, and there you go. It looks a little bit confusing, and it looks confusing because the contours don't look great unless you fill them. So you have to click that box, and now it actually looks reasonable. And what this is saying is that the highest velocities are in the narrowest region. And then in fact, you are getting some complex flow patterns due to the fact that you have this obstruction here. Okay, so those are contours. You also can look at vectors, and we're going to set that up. And these, again, velocity, velocity magnitude, tells us something about not only the magnitude of the velocity, but its direction as well. You want to zoom in, and zoom in this case, is actually the center mouse button on my machine. You can change these defaults in the settings. So there are arrows there, but they're kind of hard to see. So we're going to increase the scale, hit display. Okay, now the arrows are bigger. But they're kind of overlapping, so it's hard to see. So let's increase the skip. This means we skip some of the elements. And what you see now pretty clearly is that there's a zone of recirculation behind the obstruction. To zoom out, I hit the center button and make a rectangle going in the opposite direction. In terms of mouse buttons, you can use this to change the behavior of the mouse buttons. And if you want to zoom back out, go to Views, Auto Scale. And that's it. You can save the project and close Fluent, and we're done. You can also analyze the results, but we've really done all of the result analysis that we want to do. So we're going to skip that part, and so that means that we're done. We can close this down and move on to the problem.